Okay, welcome back. We're going to finish this lecture series by talking about the Beer-Lambert law, spectroscopy, and how we use it to determine concentrations. So the Beer-Lambert law is named after two scientists, and one of them apparently was a big fan of pubs. But okay, maybe not. I actually don't know. But the the key feature right here is that we actually get to use instruments. Some of you may actually have had the um, opportunity to play with some of these instruments already. But pretty much what you do is you have a solution that you pass light through it. And we basically determine with the instrument something known as absorbance. And the absorbance, just in simple terms, is the ratio of how much light passes through a solution. In essence, you look at the light that you're generating in the instrument, you pass it through a solution, and then you see how much light made it out of the solution. And this ratio, when you take the negative log, you get the absorbance. Now, luckily for us, the instrument does all of that for us. Like, we don't actually have to calculate this thing and figure out how many luminosity units, we're dealing with, how many lumens, like that's all done in the instrument. But what we do actually have to do as chemists is prepare solutions. And these solutions get added to these holders called cuvettes. Generally speaking, traditionally, these cuvettes are made so that the width of the cuvettes are 1 centimeter in length, and that has a particular reason for it. The cuvette is then placed into the instrument, and then the light that is generated inside of the instrument, which has a specific luminosity, passes through the sample, but only a certain amount of light makes it through. The amount of light that doesn't make it through is directly and linearly correlated to the concentration of the solute. So you can actually see by how much the light decreases in terms of its intensity with the concentration of solute present in solution. And the relationship itself is known as the Beer-Lambert law, which tells you that the absorbance, capital A, is equal to the absorptivity constant times concentration and path length. So let me show you that. Let me spell it out for you. A is the absorbance. It doesn't have units. The values actually go from 0.1 to 1 for the most precise measurements. The epsilon is known as the absorptivity constant, and it's obtained directly from the slope of the Beer-Lambert plot, which I'm going to show you in just a little bit. C is the concentration. So typically you either prepare concentration samples that you very accurately know the values for, and then measure the absorbance to get the graph that I'm about to show you. Or if you already have that information, you simply prepare the solution, look at the absorbance, and then you can get the concentration afterwards. But this also depends on the path length, because the deeper that the light has to pass through a solution, the more light is diminished and decreases in intensity. So to make it standard, the idea is that you want to see how much the light diminishes passing through only 1 centimeter of length. And as long as you use this type of cuvettes, it is guaranteed that the path length is 1. So as far as this equation is concerned, technically it works out to be absorbance equals epsilon times concentration for the most practical of cases. All right, but now let me show you what happens when you actually make different sets of the same solute present in your solvent, but you actually make it so that you have different concentrations. If you measure the absorbance of all of them, you can actually plot the absorbance versus concentration, right? And this concentration could be molarity, or it could be grams per ml, percent grams per ml. But what's not going to change is the fact that the correlation between absorbance and concentration will be a linear relationship, right? And so you should have a set of data points. This particular data point corresponds to a particular concentration and a particular absorbance, and that applies to all of these points. Now, when you do this and you get a linear regression for it, you get the equation of a line, which in this case is y equals 1250x plus 0.05. And then the correlation value tells you how good a linear fit this is. And in our case, it's fairly good. It's 0.989, which tells you that is not perfect. If it were perfect, it would be exactly 1. It's not perfect, but it's actually good. It's good, and you can work with it. By the time this gets to 0.96, 0.95, yeah, you don't even need to be told that the correlation value is kind of kind of iffy, you can already see your graph looking pretty iffy, So without the correlation, you already know that, yeah, this is not looking all too hot. But 0.98, 0.99, that's absolutely great. All right, so if you think about the Beer-Lambert law that I mentioned a little ago and compare it to this equation, well, then technically y has to be the absorbance, right? Because it's what you're plotting on the y-axis, right? Absorbance is what's plotting on the y-axis, so that's the absorbance, literally y. Um, concentration is what you're plotting on the x-axis, so that's literally the x value of the equation. And then the slope, the 1250, which is the slope of this line, is actually epsilon times L, right? These two constants that are present in Beer-Lambert's law. And then ideally, Beer-Lambert law should have no intercept. Experimentally, just due to systematic errors or just errors in general, you're probably going to have a y-intercept that's not going to be 0, but it's going to be pretty close to it, like something like 0.05, and that's fine. That doesn't change things too much. But what you can obtain from this is the value of epsilon, because once you have the slope 1250 in this particular case, you can say, well, 1250 has to equal epsilon times L, but we already know that L is equal to 1, so epsilon is literally the value of the slope of this plot. So that's what we use it for. And you may ask, well, okay, fantastic, but why? Why would we even care about it? Well, there's different reasons. One could be if you're comparing samples of different ions, different compounds, the epsilon value could actually tell you a lot about what's happening to the electronic framework of the molecule, and you could even go as far as like depicting the structural features of a molecule. In essence, since we have a lot of knowledge about the types of shapes that molecules can adopt, and we have an idea of what epsilon values are related to, by looking at the value of epsilon, you could kind of get an idea of what the shape of metal ions are in solution, specifically biological samples in proteins, which are kind of hard to isolate and get into structurally be determined. With spectroscopy, you can tell and have a at least a general idea of what the environment around your metal ion will be. So it has that connotation, right? All right, but the other thing you can do is you can actually use this value to calculate concentrations of solutions that contain the same solute, but that you do not know the concentration of from the get-go. So for instance, you could take a sample that you don't know the concentration of. You know it's the same solute dissolved in water, and it happens to have an absorbance of 0.47. So what you can do is use Beer-Lambert law and simply um, solve for the concentration, divide by epsilon and L. So absorbance will be divided by epsilon and L, and simply enter the values: 0.47 for the absorbance, 1250 for epsilon, 1 for L, and pretty much you're dividing 0.47 by 1250, so you find out that the concentration of your solute dissolved in your solvent is 3.76 times 10 to negative 4. And depending upon whether or not this plot was done with concentration in molarity units, this could be molarity. But if the plot was made with percent grams per ml, then this will be percent grams per ml as a unit. But that's pretty much the idea behind the Beer-Lambert law. So hopefully this helps you rationalize how spectroscopy can be utilized to determine the concentrations of solutions and maybe even get additional structural information. But that, of course, will be the topic of an advanced course in chemistry. Hopefully, we'll see you there. But yeah, that is it for this lecture. So I hope you enjoyed it, and I'll see you in the next one. Bye bye.